All right, in this tutorial we are covering the law of conservation of mass. And to start things out, we are going to just kind of get a definition of that, which is given in your textbook. This is a snippet from your textbook. So it states that the law of conservation of mass states that in a chemical reaction, the total mass of the reactants is always equal to the total mass of the products. So in other words, everything into the reaction is going to be the same as things coming out of a reaction in a closed system. So it looks something like this. In class, we did an experiment that was similar to this. We used different chemicals, but the same setup where we had an Erlenmeyer flask, closed system, have a stopper on it right here. So nothing from inside these chemicals here could not get out, and nothing could get in. And so we saw a reaction. We saw things that changed inside of the solution when we mixed the two. And some of you had different guesses about what might happen, whether mass would go up, go down. But in the end, we discovered that, in fact, the mass stayed the same. That what was there before is still there after, just rearranged in different ways. We also did another experiment where we reacted some chemicals that produced a gas, and that gas escaped, and we did see that the mass went down. And obviously we concluded that the mass went down because some of the matter escaped the system. So we did the experiment again, it's a horrible drawing, with a balloon, and the balloon captured the gas inside and weighed it and saw that the mass stayed relatively the same. So in way of example, let's look at the example we looked at in class, which is methane reacts with oxygen to produce carbon dioxide and water. So methane was, so this is a word equation. Methane, you'll have to remember, has the chemical formula CH4 plus oxygen. Now, oxygen is one of those diatomic molecules. So you have to remember that when you're writing it. So you see just oxygen here, and you have to remember to put O2. And the acronym we use for those diatomic molecules is Brinkelhoff, if you remember. Brinkelhoff. And those are all of the diatomic molecules: bromine, iodine, nitrogen, chlorine, hydrogen, oxygen, and fluorine. All right, and carbon dioxide, carbon, CO2, plus water, H2O. All right, so to apply the law of conservation of mass of this, we know that all of the stuff in a reaction going into it, so all of the reactants, must add up to the same mass as all of the products. And I just want to show you a kind of a ball and stick rendering here of what we're looking at. And as you can see here, methane, CH4, there's oxygen, and here's CO2, and here's water. The carbons add up. You have one carbon here and one carbon here. So the mass should be the same on both sides of the equation. I kind of want you to think of like a big, scale, those balances, that kind of teeter-totter around, and they have to be the same. They have to weigh the same. And if there's one carbon here and there's one carbon here, then they weigh the same, and so it's going to balance out. But if we look at hydrogen, we have 1, 2, 3, 4 on this side, and over here on the product side, we only have 1, 2. So there would be a weight difference here, and it's not the same. Mass in is a little bit greater here than mass out. And so to make it fit the law of conservation of mass, what we do is we balance the equation. So we try to make them the same amount of each atom. Now, what we can do is we can just add other molecules. So methane, you can see there's 4 hydrogen and there's 2 here. So what we can do is why don't we just take hydrogen, maybe I'll have to delete just a second here, I'll erase all this stuff here. this all cleared up for you. All right, so let's take water, and what we can do is we can actually just make another, just add another water molecule here. All right, so there's 2 water. Now, that fixes our hydrogen problem because you have 4 hydrogen on this side. And over here now we have 1, 2, 3, 4. So that's fixed. But now we have another problem with our oxygen. You can see that when you add water, you can only add molecules here. So when you add a molecule of water, you also add one other oxygen. And so if we were kind of tally up all of the oxygen on the product side, you would see that there'd be 1, 2, 3, 4. And now on the reactant side, there's only 2, which sort of is an easy fix. All we have to do is add another oxygen. So let's add another oxygen. And there you have it. Well, I'm going to erase all of this. All right. And here, if we just look at it in terms of what's on the reactants, remember these are all the reactants. I'll just write that, reactants. And these are all the products. They need to be the same. Mass in equals mass out. So let's count them now. We have 1 carbon. We have 1 carbon. That's balanced. We have 1, 2, 3, 4 hydrogen, and we have 4 hydrogen here. And oxygen, we have 1, 2, 3, 4, and over here we have 1, 2, 3, 4. So that would be a completely balanced equation. And so what we can do, just so we don't have to draw ball and stick models all the time, is we just tell you how many molecules just by putting what's called a coefficient out front. That's just a whole number. It can't be a fraction. It can't be a decimal. You have to put a whole number out here. And so right now you see that we have 1 CH4, and you can count your O2s. You got 1 O2, you got 2 O2s, and here you have 1 CO2, and we have 1, 2 water, 2 water. And that is it for the law of conservation of mass. Remember that it is the total mass of the reactants in a reaction are always equal to the total mass of the products. If you have any questions or concerns, please come and see me. If you have any questions or concerns, please come and ask.